Welcome to Lecture 11 in this series of lectures on statistical quality assurance and statistical process improvement. In this module, we're going to talk about using standard statistical software to do one-way random effects analyses. The particular software we're going to refer to is a product called JMP, JUMP, I'm going to call it. Actually, it's one implementation of standard statistical methodology, and there are many other software packages one might use, and it's not so much a particular package that's important as it is the inference that one can get from these packages, the methods and the interpretation of the inferences. We're going to begin with an example that comes from pages 50 and 51 of the book by Vardaman and Job. In particular, what we're going to do is use data from problem 210 that has hardness measurements made on each of 9 parts by a particular operator, the first operator, operator A. This is a scenario of the type that it's illustrated in a figure that says there's some process with a mean and a standard deviation that produces measurands. Those measurands are the hardnesses of the 9 specimens, and one operator, one measurement device, produces, as it is in this case, a couple of measurements, 2 measurements for each of those I equal 9 parts, those 9 measurands. Here's a data set, a data sheet for the JUMP software, and you can see here that part number 1 has measured hardness 3.3 and 3.2. Part number 2 has measured hardness 3.2 and 3.25, and so on. There is in this data set 9 different parts, a total of 18 different measurements. It's important for how at least this software interprets this data sheet to notice that part has been set as a categorical variable. Hardness has been set as a measured variable. Here's a screenshot of a dialog box that was used to get the analysis that we're going to discuss here in a second. What's particularly of interest to those of you that are actually using the JUMP software is that it's the fit model routine that's been used. The response is the hardness. Y is quote unquote Y is hardness, and the part is being used as a explanatory or factor variable. Here in this dialog box where parts has been placed, it's noted as being a random factor, or a random, the part effects as being random effects. That can be set using the dialog under this attributes red triangle down below. If you tell that dialog box to go, you get an analysis that looks about like this. You get a report from the JUMP software that looks like this. What I want to focus on here is that one is provided with inferences for so-called part random effects and quote-unquote residual random effects. And in fact, one gets confidence limits. They're confidence limits for variances, so if you want the corresponding confidence limits for standard deviation, you must take the square roots of those endpoints. In this context, part variance is this sigma squared for the process, and residual, quote-unquote residual variance, is sigma squared for the device. It's the sigma squared. This is sigma squared mu. This is sigma squared in the general one-way random effects model setup. The point here is that this comes out straight away from a call to a routine statistical package. A second, and one can, I note here that the lower end of this confidence interval for this variance is negative. Of course, no variance can be negative, so one would replace that with 0 as one tries to interpret the output. A second example here is the case of problem 212 of the textbook. In that, 3 weight measurements were made on one piece of paper by each of 5 operators. So what we have here is one measure n, which is the weight of that piece of paper, that each of 1, 2, ... down to 5 operators measure. That is, there are 5 devices here, each operator having his or her own bias, producing 1, 2, 3, 1, 2, 3, 1, 2, 3 data values for each operator. Again, in this context, in the one-way random effects model, mu is the measure end plus the average of all operator biases. The variability sigma measured by sigma sub mu is the variability in the biases, and the sigma is this repeat variation that one has for a particular device, for a particular operator. So here for this setup is the jump data sheet. As I say, operator 1 has 3 measurements, operator 5 has 3 measurements. And the basic intention here is to quantify how variable these measurements are within an operator relative to how much difference there is between operators. Here's a dialog box for setting up this analysis. Again, the operator in this case must be set as a categorical variable. Weight is a measured variable. It's the response. And again, the operator is set as a quote-unquote random factor by making use of this attributes menu down there. The output of this analysis is again a jump report, and again I'd like to focus on this table of estimates down here, where there are confidence intervals for 2 variances, 2 variance components. There is the variance component between operators, so that's a sigma squared for operator biases, and then there's a sigma squared for device. This bit is a reproducibility variance. This is an interval for a repeatability variance. Again, if jump reports a negative variance, of course you replace it with a 0. Here is then what one knows about, or what one thinks one knows about the standard deviation of the biases. It's on it with 95% confidence. That sigma is no bigger than about 0.007, and the repeatability standard deviation is between 0.006 and 0.014 with 95% confidence. This is a case where this is where the reproducibility variation is actually apparently smaller than the repeatability variation. That has important practical consequences. It says that if I don't like imprecision of measurement that I'm faced with, it's not going to be good enough simply to make operators be more consistent. That is, operator to operator. When reducing variability in operator bias is not going to completely deal with measurement variability. Rather, I'm going to have to address this issue of repeatability, and that often requires capital expenditure investment in fundamentally better measuring equipment.